Okay, maybe we should, we'll make a start. So good morning, everyone. Welcome to the third day of our meeting. First speaker this morning is Philipp Habegger, who's going to speak about the Dynamical Schinzel-Zassenhaus Conjecture and the transfinite diameter of trees.
Okay, thank you, Jonathan, and thank you for the invitation here to speak. So I'll talk about joint work with Harry Schmidt in Warwick at the moment, or is Warwick now. And so I'm not going to talk about O-minimal geometry in this talk, but I'll talk about an ingredient that's often used in connection with O-minimal geometry to prove things about unlikely intersections, and that is, in the end, lower bounds for heights. And as we saw in geometry talk yesterday, heights play an important role in various parts of this field. So let me just recall the most basic height that we'll need is the absolute logarithmic of a height. And you saw a definition for the rationals yesterday, but I'll use it on the field of algebraic numbers. And in particular, well, I can plug in any algebraic number, and it's normalized in a way that if I take the dth root of 2, then I get, well, I get log 2 because it's the logarithmic, right? And it's absolute, so at one point I divide by like d. This is the, we'll see a definition in just a moment, but this is the height I'm going to work with. And other notable points are roots of unity. So if I plug in a root of 1, then the height is 0. And the height, for example, of 0 itself is also 0. In fact, the only algebraic numbers of type 0 are the roots of unity and 0 itself. And so lower bounds for heights, well, the main conjecture in this area is that the height, if it's positive, cannot be quicker than like 1 over d, constant over d. This is what's sometimes known as the Lemur conjecture, even though Lemur never stated this. In fact, stated the converse as a problem. Conjecture states, what's called now the Lemur conjecture, is that there exists an absolute constant, strictly positive, that if alpha is a algebraic number, and we assume that its height is positive, or equivalently that it's not 0, and not a root of 1, of degree d, then its height decays at worst like 1 over d. So this is this decay is the quickest one can expect. Right? And so the conjecture is open in this formulation, and but we know quite a lot. So the best possible asymptotically height lower bound that we have is to Dobrovolsky. And it's almost 50 years old now. And it says that height is at least constant over the degree times some logarithmic stuff. So there have been improvements at the level of this constant after Dobrovolsky's work by Guttini, but this exponent 3 and log over log is still state of the art. So it's almost a conjecture, but it's well, it's not yet a conjecture. But I'm not going to say more about this situation here. But what I want to say, I mean, first I want to explain some parts of the title, and I want to say something about the Schinzel-Zassenhaus conjecture, which is related to the Lemur conjecture, which is also now a theorem, and how it relates to what I'll say later. So this was a beautiful result by Dimitrov from 2019. And the setup is slightly different. So we take an algebraic integer. Explain in a moment why. And we have the same hypothesis. It's not 0 and not a root of 1. then it doesn't get a lower bound for the height, but for the maximal complex conjugate of alpha. So they're taking the maximal embedding of alpha into the complex field, and well, I'll take the logarithm of the absolute value of this embedding. And the theorem that he proves, this is positive, and it's at least log 2 over 4d. So again, a reciprocal decay. So in a sense, this is best possible now because well, we have these kind of examples that have exactly that 1 over d decay, right? But instead of taking the height here, take the maximum of the complex embeddings of alpha. Whereas the height is somehow an average. If you just look at algebraic integers, it's the average of these guys here divided by d. And this is a pointwise lower bound, right? So for everything. So in a sense, it's yes, the maximal is bound from the lower. And as a corollary of this result, of this inequality, one gets that the height, because the height is the sum over these here divided by d, get a lower bound that is quadratic 1 over d squared times a constant. So not Dobrowski style decay, but 1 over d squared. But this is here is best possible. And this is what was known as the Schinzel-Zassenhaus conjecture. But it gives us a polynomial decay in the degree. And these polynomial decays are often very useful in applications to unlikely intersections, where you need a lower bound for the height that can often be translated into an upper bound, into a lower bound for the degree. If you know something about the height, you know an upper bound, then you can apply point counting techniques. Okay, so that's the kind of Schinzel-Zassenhaus part of my talk, and I also want to say something about dynamics because this is somehow the classical V height. I want to say something about dynamical heights. So which will be arithmetic dynamics. And here are slightly more general. So F is a number field. And F, lowercase f, is going to be typically a polynomial in one variable t, and the degree of f is at least 2. Many things can be done for rational functions as well, but I'll stick to polynomials and just mention things about rational functions on the way. Right, and so any polynomial will define a dynamical system just by iterating, by plugging in values into iterates of f. Alpha is in the field extension of the base field, then the orbit alpha, that's just the set, the forward orbit of alpha under the polynomial f. We'll see some examples. So this is, it can be an infinite set or it can be a finite set. And just as in this setting, there's a height function that's kind of compatible with the system. So let me take a place of f, or f prime. It's a matter at this point. And alpha is now some element of completion. And locally, you can define following height with respect to f. This will just be, well, you look at iterates like this. Take the absolute value with respect to the place, and then logarithm, and we'll take, it's often, so we'll take the positive part of the logarithm, and then divide by e to the n, where n is this index, and then we take the limit as it goes to infinity. So this is a fact that this converges for all alpha here in this completion, non-negative, no numbers. Example. So the basic example, t squared, and then iterating t squared is simple. And what you get is that the local canonical height is just log plus the absolute value of alpha with respect to v. So log plus just means the logarithm of the maximum of 1 and the argument here. So it's always going to be and these are the local heights, and we can patch them together to get the global height. Global height is then just the sum over now alpha is allowed to be any finite extension of the base field, and it's going to be absolute. So we divide by field degree. We take a sum over places of f prime, and then we take certain local degrees here. And then we take the local heights. So if you plug in t squared, you recover exactly the absolute logarithmic Bay height. I didn't write down the definition before, but it's exactly what you get here. You just have log plus and the absolute. But what's interesting is if you take other maps, not t squared, but more complicated things. And we also have a kind of a characterization of this is always going to be non-negative. We have characterizations of those alpha that have zero height. So height 0 if and only if, and it's a theorem, if and only if the orbit of f under the action of alpha is finite. It's one direction. Right to left is simple. If the orbit is finite, you look at what happens here. When you're stuck in a loop here, eventually, this numerator is going to be bounded, but the denominator goes to infinity, and so the limit is 0 locally at all places. That's one direction of this equivalence. Other direction uses a global argument, but is also not difficult. But this characterizes those with height 0, and it generalizes the fact I mentioned about being height, just roots of unity in 0. The only algebraic numbers where the orbit is finite under the squaring out. And so you can do the same kind of computations. And you can also cook up a conjecture, a dynamical labor conjecture, where instead of taking the V height, we take this local canonical height. Sorry, the local canonical height here, which is sometimes also called the Call-Silverman height. And if the height is positive, conjecture that it decays at most like constant over the degree. There's a dynamical labor conjecture, which is of course also open because formally it implies it would imply it. But there are also partial results. Manage this. So here, dynamical lemur. So if the canonical height is positive, then it is at least some constant divided by degree, and here d is also degree. So partial results here. By Matt Baker, which essentially say that this is generically what happens, but worst case is you still get a lower bound that's exponential in the degree. So this is from around 2006, and works for rational functions in general, not just for polynomials. Okay, So that's kind of the setup, and this is what we're looking at, and we're going to try to again get lower bounds for the height by bypassing through something like this dynamical Schinzel-Zassenhaus question, like Dimitrov did, and then get at least a polynomial lower bound in the height. So I need one definition before I can state our result. So f is still going to be a polynomial, and this is a concept from dynamics. F is postcritically finite. See that? If for all critical points the orbit is finite under F. So this is just the zeros of the derivative of F. It's the Algebraic closure. If all these critical points have finite order, then we call F postcritically finite. Examples here that you can write down. E squared, because the only critical point here is 0, and of course it gets mapped to itself. Another example is t squared minus 1. Here 0 is mapped to minus 1, and minus 1 is mapped back to 0, so they get swapped. ECF t squared minus 2. It's a bit more complicated here because 0 goes to minus 1, minus 2, and minus 2 goes to plus 2, and plus 2 goes to itself. So the orbit is also finite with the critical point, but it kind of ends up in a loop after 2 steps instead of after. And if you just want to stick to the quadratic case, if you look at polynomials of the form t squared plus c, and if you impose that the critical point returns to itself after n steps, you get a polynomial in C of some like 2 to the n power degree. And if you're a root of this polynomial, you'll find C that gives you a postcritically finite map. So you can find many of these, but only countably many, countably infinitely many, right? Because you get for any n you get polynomial, and you also have to show that you get actually infinitely many, but most countably. They're all algebraic as well. In a sense, there has some similarities to being a curve with complex multiplication, because they're kind of moduli spaces, a countable algebraic set. Okay, but generically for random C here, this is not going to be. It's an arithmetic restriction of the thing. So just look at this example. T squared minus 2 when it's 1/2 is not PCF. Because, well, you look at what happens at the orbit of 0, 2 adically explodes and can't find it. Okay, so here's the theorem. We wanted to upload it around this week to the archive, but it's not completely ready yet, but I hope weeks. So we look at a certain class of polynomials that are PCF, and our polynomial has the following shape, so it's going to be a bit more general than t squared plus c. So we're going to look at to the d plus, so this is sometimes called centered. So there's no one term. We assume that its exponent here is power over prime. And yeah, should mention this. It has to be an algebraic. Coefficients have to be algebraic integers. Right. So here. this equation will give you a monic polynomial in space with infinite many algebraic integers, where actually you have PCF map. F is assumed to be PCF, according to the definition above. And okay, so this is our general result. I'm going to state something slightly more restrictive, but we also have a result for PCF maps in general, such that all critical points of F are periodic. PCF is a bit strong, is a bit weaker. All periodic points are pre-periodic. So this could be pre-periodic, you end up in a period. We're going to ask that all critical points are periodic. And second, this is just a technical assumption now for the talk. The base field is unramified above P. So that's hypothesis on F. We can construct, we can produce them by looking at this kind of example here. We can also look in higher degree, but degree has to be a prime power. Okay, so what's the conclusion? Then if alpha is algebraic, and well, we only say things about points of positive height, so we assume that the orbit is infinite, and this is just sometimes also called wandering. Then the height alpha, it grows at least like 1 over v squared. The constant here depends on F and base field. So similarly like over there. And in fact, we bypass through the local estimate. So if F is wandering, so this is the second statement, plus integral then the local canonical heights, the local parts that like sum up to the height, the key at most like 1 over d. So as in this like Schinzel-Zassenhaus setting, we prove something like this, and then we deduce this, right? Just because the height is the average and the infinite places contribute. So this is just the maximum of the infinite places. And so we get an extra factor 1 over d because at the end we divide by. Here we have to really work with integral points, and then we can go to algebraic. Well, also non-integral points because the finite places also contribute here to the height. Easier to handle in this setting. So it's here in this setup, the infinite places are the ones that are interesting to look at. Okay, so the theorem, as stated here, it covers t squared minus 1, of course also t squared in a sense, because but not, formally speaking, not t squared minus 2, because, well, periodic, the critical point here is pre-periodic, but not periodic. It ends up in a loop after steps, and also not things that are not even PCF. But a lot of examples here. So, are any questions at this point?
Do you think the log squared should be recoverable as well, or is it not here for a different reason?
Excuse me,
if I'm so Dimitrov had a log squared over 4d and a log squared over d squared.
Log.
It's a log 2. I'm silly.
It's log 2. Yeah. But that's the numerical. So so the question of if we can get the numerical constant here, no.
But in the case of t squared, did you recover Dimitrov's theorem?
Yeah, not with the constant.
Okay.
Up to the constant. And we can get you can get a slightly worse constant. I can say if you think about that. Okay, so that's kind of the result, and guess I want to say something about how finite trees and the transfinite diameter play into the proof. All right, so this will be the next part. Finite diameter. It's also called, or equivalently, it's also that the capacity, take a compact set plane, and the capacity or transfinite diameter is, well, the diameter is just what you get if you max over differences of elements in K. Transfinite diameter looks at more general things. So we take not just one point, but one point, but many points. And then look at the geometric mean of the differences of these points. So we have to take the geometric mean, which take a root here, and the root is n choose 2, the number of terms. Now this expression here depends on n, right? For any n, I get this maximum. For n equals 2, I get exactly the diameter of the set. For n equals 3, I get something that looks a bit more complicated, but will be smaller than the diameter in general, because we're taking geometric mean. And if you take n equals 4 points, you get something even possibly smaller. So this is a sequence that's not increasing. The limit of this sequence as n goes to infinity is the transfinite diameter. So this always converges. Finite set, you get 0, of course, because eventually the points have to match up. This is most interesting for compact sets that are sufficiently big. So just as an example, the transfinite diameter of either the units, unit disk or unit circle is 1. Essentially, it only depends on the boundary that's exposed to point at infinity. Transfinite diameter of the unit interval is 1/4. And so transfinite diameter of interval of length 4 is exactly 1. So they both have transfinite diameter 1. But in general, if you take some natural looking objects like a square with length, side length 1, you get something very complicated. So this is a tricky thing to compute in general. But in this dynamical setting, it'll be very useful because it will be easy to compute often. So the main example comes from, well, at least for this talk, comes from dynamics. We take a polynomial of degree 2 that is monic. Then we can construct what is so-called Julia or filled Julia set. The points complex plane with bounded orbit. Orbit is bounded. So, for example, with the squaring map, you get exactly unit disk, closed unit disk. Because if you're outside the closed unit disk, you keep on squaring, you go off to infinity. If you're inside, yeah, you'll stay inside forever. This is precisely the closed unit disk for the squaring map. And in that case, it has transfinite diameter 1. This happens to be the filled Julia set for t² minus 2, is also not part of C. It also has transfinite diameter. In general, as long as you take something monic, transfinite diameter of this set will always be 1. These sets can be very complicated. So this is what I attempted to do before my talk. I attempted to draw what it looks like if you take t² minus 1. So what you're seeing here actually is an approximation of the boundary of the Phil-Julius set. Like whatever is inside is the KF. So here is 0, critical point, -1, image, the critical value. So this equality holds for all. Okay. Right. So now come to an ingredient. This is a theorem that's a long history by work in his proof of rationality of the zeta functions of varieties over finite fields. The version here is due to Polynomial vectrondias. It's a slight special case. And this will be the kind of the main gateway from analysis to number theory. These kind of arguments. We'll see how it works together in a moment. So we take a power series in 1 over x. So the reason why we take power series in 1 over x instead of x has to do a bit with the fact that the connection of these transfinite diameter with the capacity with respect to point at infinity, and essentially we're looking at neighborhoods of infinity. So we're developing into 1 over x. It's just a technical point. We assume that things phi converges for all large complex converges absolutely for all large complex numbers. So it converges absolutely in the neighborhood of infinity. And second, phi extends and meromorphically or holomorphically to the complement of some compact set with transfinite diameter less than 1. So it extends. It doesn't only just converge near infinity, but it can extends to holomorphic map by on some larger set that's the complement of something of small transfinite diameter. And the conclusion is that in this case, power series was actually a rational function. So it's a rationality statement. So there are versions of this where you can replace the integers by a more general ring of S integers in a number field. We also have to take into account what happens at finite places, possibly other infinite places, but for purposes of the talk, I'll just mention this basic version of the theorem. Am I allowed to use this one here too? Or? Okay. So this is Dimitrov's approach to Schinzel-Zassenhaus. So let's look at what happens in this example here. So we assume what we have. Let's assume we have this F here. This is what the Phil-Julius set looks like, at least the boundary. And now we have some algebraic number where the local canonical height is small. So we have a lot of conjugates. And having small local canonical height essentially means that we are close to this Phil-Julius. There also could be points inside. This is all things. Say alpha is an algebraic integer, and they're all infinite places. We have a small local canonical. So the thing to note is that the local canonical height vanishes if and only if the point is in this set. So the vanishing radius of this function is it's complicated fractal. But if it's small in ascent, morally speaking, that means we're close to the Julia set, at least close to. Could also be inside. Okay, and so the construction, the map, or the power series that one looks at is the following product. So we take alpha 1 to alpha d. They're the complex embeddings of our algebraic number alpha. And then we look at 1 minus f. This is technical here. We look at a finite product like this, where well, each factor is something of degree 0. It's a rational factor here. We take a certain iterate of alpha I here in the numerator, and a certain other iterate of alpha I in the denominator. We take the product over all arguments here. So the choice of k and l is a bit technical, but they're suitably chosen in function of x. So you can think of them as fixed in terms of the given data here. So this is just a rational function. There's no hope of getting any information out of the theorem because it's a priori irrational. But what one does here is you take a certain root of this function, take the pth root, which is now in general no longer going to be irrational, but it's going to be a power series. And what happens is, well, the suitable here that I'm pushing under the rug can be exploited to get an integral power series here. In general, you'll have a problem at the prime p. Taking a pth root will introduce the powers of 1 over p in the Taylor expansion. But by a suitable choice of k and l, you can avoid that. That works exactly. It's somehow similar in the classical H-flag of Dimitrov. So a priori, it's a rational power series, but actually, it's a power series. It has to do with the fact that, well, this is kind of a general observation that in this PCF case, where the polynomial's prime power degree, it looks like it's composed with Frobenius is composed with some other polynomial, so there's a zero derivative. Essentially, this is what goes into these kind of computations. Okay. So what is the goal now, or the plan? So we have our power series, and it obviously converges for large values, and we want to find a suitable k with, first of all, everything here that can contribute to 0 or whole of our of the rational part here is contained in K. So all the points that kind of where the rational function here under the root is valid are contained in K. And second, K is a topological tree, or finite topological tree. And third, we want that the transfinite diameter K is less than. So why tree? Well, think of it this way. If we can somehow connect these alphas here to a tree, then what's under the pth root here will be well defined on the complement of this tree. And it will also be well defined at infinity because we're looking at 1 over. So it will be well defined on some simply connected domain, which is the complement of the tree in the Riemann sphere. Now, by basic monogamy theorem, you can extend pth root from a neighborhood of infinity to the complement of the full tree. And that will, of course, apply to satisfy part 2 here. hypothesis 2 in this theorem. So these two together imply that phi is rational by polynomials. Right? And as soon as phi is rational, because it's already a P3 to start out with, that means has to be some conspiracy among these zeros and poles that they cancel out, right? Otherwise, you would never get a rational function. So if this guy here matches up this guy, it's easy to see that alpha has to be a finite orbit. This is kind of a formal step here. Alpha is. In this case, of course, if the height is 0, there's nothing to expect. So this is the plan so we need to construct like a tree that contains prescribed points, and the tree has to have small transfinite diameter, less than 1. Okay, so I see the mistake I made because now this last part is fixed. Okay. So where do these trees come from? Next section is Hubbard trees. So this is a general construction that works for PCF polynomials, postcritically finite, and as usual, the degree is at least 2. And I'm going to assume just for safety that it's also monic. And this is a construction that goes back to the 1980s. In lecture notes by Hubbard. They constructed a finite tree with a complex plane called the Hubbard tree. And this Hubbard tree, it contains critical points in everything that's in the forward orbit. So it contains all orbits of all critical points. This is a finite set by hypothesis. All these orbits are finite, and they construct this tree. Of course, it has additional properties because you can always construct a tree like this with some nice properties. I'll come to these properties in a moment. Two properties I want to emphasize is that first, the Hubbard tree is contained inside the Phil-Julia set. And second, the tree is mapped to itself under the action of F. So it's K is already mapped to itself under F, but this subset of K will also be mapped to itself under F. Let's look at just two examples or a few examples. T squared, this is kind of the trivial example. There's only one critical point. The orbit of the critical point is just 1 point. And here the Hubbard tree is also just 1 point. 0 point. It's one vertex and 0 edges. More interestingly is T squared minus 1. So here, well, it's still quite easy to write. To guess the tree, it's just this integer here. This is Hubbard tree of T squared minus 1. You can check that it's mapped to itself under F. It's easy to see. It's also contained. So here, crucially, transfinite diameter of the Hubbard tree is what's the length of this divided by 4? It's less than 1. So this is going to be kind of work in our favor. It's already less. That's already something. But of course, this tree is not going to be enough. Like, I have all these points here. I want to find a tree that contains all these points. And I just have this one tree here, which is just a one branch. So it's not going to be very helpful. So what we actually do is we look at preimage of the Hubbard tree under the map F. So consider, so S is some integer. Consider it as some parameter for the moment. We take the preimage of the Hubbard tree under the F, the iterate here of S, of F. Okay. It's not that easy to imagine what happens. So in this case, nothing happens. But in this case, it's not so easy to imagine what happens. I tried to plot this. Let's see if this works. Okay. It's my teleprompter. So the tree here, that's what the red line here is of the Hubbard tree for S equals 1. And if I increase S, I start getting branches that go off here. I think somehow this is for S equals 5. It kind of starts filling out here. Further. This is H. So this is kind of, in a sense, it's a combinatorial approximation of this filtering as S goes becomes larger and larger. Now, okay, so we know something about the transfinite diameter, at least in this example. Now there's a neat formula that says the transfinite diameter of the preimage of a set is always going to be the transfinite diameter of the original set taken to the 1 over d to the s. So this is the degree of the s-fold iterative of f, and we take this root here. So as s increases, the tree is going to get larger and larger. The transfinite diameter is going to approach 1, but it's always going to be strictly less than 1, which is kind of, again, it's nice to know that because of this condition here. The other thing I haven't mentioned yet is, well, what is a preimage even? There's the preimage of this tree is always going to be tree. It's always connected. The reason is that the Hubbard tree was constructed in a way that it contains all critical values of all iterates of F. That just follows from the fact that F is PCF and this property here. So the image, so H contains all critical values of all iterates of F. So the preimage is connected to, you can also show it's a tree. Okay, so this is a tree for all S. We can say something about the transfinite diameter of this preimage here. And well, it's going to be strictly less than 1 in the interesting examples. There's a final kind of gadget that's missing at this point, and we need to somehow control the combinatorics of this tree. This one here. So this condition here tree is mapped, the first tree is mapped to itself under F, implies that the trees are nested. They really become larger and larger. It's at least set theoretically. And it also implies that F induces a sort of Markov map on the edges of the tree. There are finally many edges. And each edge, as you walk along one edge of the Hubbard tree, and if you plug it in F, you'll walk along one or possibly more edges on the tree itself. Here in this example, just one, but in general, if you walk along one edge, you plug it in F, you'll walk around several edges. And that will give you a Markov map on the edges of the tree. Give you a matrix, and the spectrum of this matrix tells you something about the combinatorics of this tree. So this is what Thurston's core entropy. F is the maximal eigenvalue. In absolute value. Yeah. We'll call it rho of F. So it's an integral matrix. Its spectrum of characteristic polynomials. Integral monic polynomial, so it has to have only have a root at least one. Basic theory tells us that this core entropy is always at most the degree. And what we show under hypotheses that are subsubbed in the theorem. So that's where the hypothesis that the critical points are all periodic. That's a bit stronger than PCF. You can also formulate it even a bit stronger, which is hyperbolic in PCF. In our case, there's a slight gap in the spectrum. So the largest eigenvalue in absolute value is less than degree. And that gives, in a sense, that gives us some leverage over how this tree grows, how the diameter of the tree, for example, grows. For example.
You didn't put the alphas yet on the tree, right?
Not yet.
Okay.
Good point. Yeah, we're coming to that. We conclude that the diameter here it grows exponentially in S, where the base is entropy. It's going to be less than degree, and the number of edges Fs is always going to grow something like the degree to the S. So this cannot be. So the number of edges will always grow like a e to the S. Well, maybe except if you have no edges to start out with. But the diameter will grow asymptotically slower than the number of edges. So in a sense, the graph of the tree will be easy to traverse. So it'll be sufficient to get from one side to the other because we have this. And now, Jacob rightly put it, that we have not yet connected the conjugates to the tree. And so the game is to choose S in a suitable way so that we kind of fill out the Phil-Julia set as optimally as possible. You choose S somehow in the order of magnitude log D. And then the last step, so you'll be close enough. There's also going to be a small like ear here, and then you can connect. Well, here it's a bit far, but you'll be able to connect the conjugates to this S-fold Hubbard. By choosing S suitable, not too large, not too small, you can arrange it so that the connections are not going to be problematic. So in the application, we choose S of the order of log D, and D, the number of points actually is 2D, doesn't really matter about log D. Okay.
You have to use some like additivity of the capacity or something because you're connecting.
That's the other point. Yeah, I'm not going into how to, we actually then compute an upper bound for the capacity. But in a sense, well, if you look at the definition, which I already erased, I think, kind of reminds you of a van der Waals matrix. So we use the structure coming from the fact that, okay, we know that what the tree looks like in the end. And we know that a lot of points here, for example, on this stretch will be close to each other. You'll be able to exploit that using kind of the structure of the van der Waals. So I'm not going to go into that part. That can be, for example, used to give a slightly weaker version of this theorem of Dubinin that Dimitrov used in his proof. So he, in his case, in a sense, the tree, the Hubbard tree is just a point, right? And the Phil Julia set is a unit circle. And in his case, so what in his paper he calls it hedgehogs, right? A hedgehog. The tree is just a star-shaped tree that kind of rays out from this point, and these are the alphas here. And Dubinin's theorem gives you an upper bound for the transfinite diameter of these star-shaped trees here. The technique we use
is for the star-shaped. This theorem gives you that.
Dubinin's theorem gives you, that's where the log 2/4 comes from. The quality of this bound is due to the quality of Dubinin's results. So the techniques we have here can also give the right decay rate for the transfinite diameter of these guys here, but with a worse constant, numerically worse constant. So Dubinin's theorem is that's the log 2/4. Okay, maybe let me just close by what is by subsumming what we show. Actually, the construction of this tree. F as above. You fix a finite set. We assume we have a finite set in the complex plane, such that the local canonical height on this finite set is decays like 1 over the number of points in the set. So this A will essentially be these 2D points that we use. The number of points will be 2D. That means that the points are somehow close to the Phil Julia set. Then there exists a tree, finite tree. K, in the complex plane that contains the set. And the transfinite diameter of the tree is less than that. So F as above, meaning as in the hypothesis of the theorem. So all the critical points are periodic. The statement is actually false for, interesting enough, for t² minus 2, which is, in a sense, extremal in all this, because here the rho is exactly 2. And so the diameter grows exponentially in S, which is a problem. Okay, so that's kind of the tool we need then to connect to Bertrand-Dias, Bertrand-Dias. And then that trick shows that we can, if the height is small, then it has to be periodic.
Yes, so A is a subset of K in the proposition, right? Is the conclusion.
Here, or
Yeah.
A is a subset. That's right. Yes, thank you. The tree contains all points of A, and then we extend the function of the complement of the tree, which is simply B. Okay, so maybe as a final remark, I said at the beginning that all these PCF maps behave like CM terms, CM varieties in some sense, but not in all senses. I impose that the coefficients are algebraic integers. But in general, there are PCF maps that have honestly bad reduction at finite places in contrast to the CM billion value situation. Thanks for your attention.
Questions?
So the conditions you impose on F, I guess both or all of them, are they necessary for the proof or for the statement?
Okay, so for the proof.
Okay, so in general, like an arbitrary rational function F, you expect the same result.
Well, I guess we expect this here. So if you mean by the same result, yeah.
But not the second one.
Okay, for the tree, the construction of the tree, I'm not sure. Yeah, so that the arbitrary rational function can have very complicated dynamical properties that disappear in the polynomial set.
But I meant more about the 1 over d, the max thing. If you impose some sort of integrality, you expect that as well?
Yeah, I would probably conjecture that. Yeah.
Okay, cool.
Where did unramified above P?
Okay, that comes into the. So that comes into the proof, especially when we show this value stuff. But luckily, if you have t squared plus c, and if it's if 0 is periodic, then unramified above 2 is for free. That's the theorem.
So the bounds you get, I mean, for the Schinzel version is super tight, and then you get pretty good bounds for later. Are there known results, or do you expect results in more generality if you relax this? Like, really, for like in this, you just need 1 over polynomial in the.
Yeah, as far as Harry and I have a previous paper that we tried out these techniques using Dubini's theorem, but as far as I know, these are the first results where we have polynomial decay. So Baker's result that I mentioned at the beginning has, in a sense, generically the lower bound should be 1 over d, but there can be exceptional points where the lower bound is exponential even than d. So it's somehow with a small number of exceptions, you get the expected bound.
Yeah, because 1 over polynomial, and usually you can get just from point counting.
Okay.
In a billion values, but here maybe it doesn't work because it's like you have only a squaring map F, right?
Yeah.
You can get many points of small height, right? Because F squares.
Yes, but the problem is that if you apply F once, you're doubling the height each time. Yeah. So that's why in this Baker result, it gets a lower bound outside small set. But if in the worst case scenario, if you're inside the set, you have to kind of iterate as S times, where S is essentially cardinality. That will kind of make the height explode.
Okay, so even with a much weaker version of Schinzel, you don't know any. There's no more general results than this.
I'm not sure if that. Yeah, I'm not aware of any results where you have a polynomial lower bound.
Okay.
Any other questions? Okay, let's thank Philip